Adaptive optics. This system uses a flexible mirror and a laser-created artificial star to measure and correct atmospheric distortion in real time, essentially de-twinkling the stars for sharper images. Lucky imaging. This involves taking many short-exposure photographs, then combining the sharpest ones taken during brief moments of atmospheric stillness into a single, clearer picture. Radio astronomy. Telescopes that observe radio waves, which are much less affected by the atmosphere, can collect data without worrying about twinkling at all. All of this effort to see stars as they truly are reminds us of our unique perspective on the universe. The stars aren't changing. We are the ones inside the snow globe, and the air we breathe creates the beautiful illusion of twinkling. The psychology of stargazing beyond the science. Stargazing has a powerful psychological effect, awe and perspective. Looking at the vastness of the night sky can induce a state of awe, which has been shown to reduce self-focus and help put our daily worries into perspective. This can lead to increased feelings of happiness and well-being. Physical relaxation. Stargazing in a dark, quiet environment can shift your nervous system into a rest and digest state. This lowers your heart rate and blood pressure physically, calming your body. Mental stillness. Focusing on something as vast and beautiful as the stars can function like a form of mindfulness meditation, slowing down your thoughts and promoting a sense of presence without any special training. Stargazing can also help reset your circadian rhythm, as exposure to natural darkness signals your body to produce melatonin, the hormone that helps you sleep. Ultimately, the simplicity of stargazing, even if you only see a handful of stars, can be a powerful act of connection, reminding us that we are part of something vast, ancient, and endlessly magical. If you were to leave Earth and look at the night sky from somewhere else, would the stars still twinkle? The answer depends entirely on the atmosphere of your new location. On the moon, there is virtually no atmosphere on the moon. From its surface, the stars would not twinkle at all. They would appear as perfectly steady, silent points of light, even during the lunar day. On Mars, Mars has a very thin atmosphere, only about 1% as dense as Earth's. So, while a subtle twinkle might be noticeable near the horizon, most stars would appear surprisingly steady. Stargazing on Mars would be like observing from a mountaintop on Earth, clearer and with much less flickering. In space, astronauts. On the International Space Station, or telescopes like Hubble and the James Webb Space Telescope, which operate in the vacuum of space, see stars as perfectly sharp and unwavering points of light. The beautiful poetic twinkle is something uniquely earthly, a product of our own atmosphere. This reminds us that twinkling isn't a universal feature of the stars. It's a feature of our perspective. The stars themselves are constant, but our location on a planet wrapped in a constantly moving atmosphere adds a beautiful, subtle signature to the view, the psychology of twinkling. While the science of twinkling is fascinating, its magic lies in how we experience it. There's a timeless, almost wired-in feeling of awe that comes from watching the night sky. Experiencing this kind of awe can lower activity in the parts of our brain associated with self-focus, helping us put our daily worries into a broader perspective. Stargazing is a form of passive meditation. It slows down your thoughts, relaxes your body, and can even help reset your circadian rhythm, preparing you for sleep. The stars don't judge, they simply shine. And whether you're contemplating the vastness of the cosmos or simply enjoying the sparkle, the stars twinkle all the same. This simple act of looking up connects us to an ancient ritual, a silent conversation shared by everyone who has ever looked to the heavens. So, the next time you see a star twinkle, remember what you're seeing, a rare and beautiful interaction between a photon, our unique atmosphere, and your own eyes. You are not just an observer, you are part of a cosmic story, and the twinkle is a gentle wink from the universe, just for you. When starlight enters this churning soup of air, it bends or refracts. This is what happens when light changes speed as it passes from one substance to another, like from the vacuum of space into our denser atmosphere. Think of it like a spoon in a glass of water. It looks like it's snapped in half at the surface. That's refraction. The atmosphere is full of countless tiny pockets of air, each with a slightly different density. Every time starlight hits one of these pockets, its path bends just a little. Imagine looking at stars from the bottom of a swimming pool. If the water is still, you see the stars clearly. But if someone starts doing cannonballs, the ripples and splashes make the stars appear to wiggle and shimmer. The atmosphere works the same way, creating a constant ripple effect that makes starlight jiggle as it travels to your eye. a subtle cosmic shimmer, while the troposphere does most of the work. Higher layers of the atmosphere also contribute to the twinkling effect. The stratosphere and mesosphere are calmer, but still have temperature differences that can slightly affect the path of starlight, especially for stars near the horizon. It's like adding extra layers of frosted glass over a lamp. Each one adds a new flicker until the final glow reaches your eye with that familiar shimmer. It's also important to note that this atmospheric bending of light doesn't just cause twinkling, it can also slightly shift the apparent position of stars. The twinkling of a star isn't just an atmospheric phenomenon, it's a personal message from the cosmos. It's the final, brief chapter in a photon's long and epic journey. A photon is a tiny packet of light. It has no mass and travels at the speed of light. Its journey begins deep inside the core of a star, where nuclear fusion creates unimaginable energy. From there, it begins a long, erratic fight to escape the star's surface, bouncing around for thousands of years before finally breaking free into the vacuum of space. Once in space, the photon coasts for millions or even billions of years. Think about that. The light you're seeing from a star 100 light years away started its journey around 1924. It was already on its way before television, jet planes, or the internet even existed. After its immense peaceful voyage through the cosmos, the photon finally encounters its biggest obstacle, Earth's atmosphere. We've already discussed how this swirling sea of molecules bends and distorts light. From the photon's perspective, this is like running a straight line through a crowded room of dancing people. It gets jostled and nudged, and by the time it reaches your eye, its path has been bent just enough to create a little wobble, a twinkle. Your eye is a remarkable thing, capable of detecting a single photon in perfect darkness. When that one lonely particle of light after a lifetime of travel hits a light-sensitive cell in your eye, your brain interprets the signal as a star. It's a handshake across the cosmos, a physical interaction between you and a distant celestial body. In this way, when you look at the night sky, you're not seeing the present. You're looking into the past. Every star is a snapshot of what it looked like years, decades, or even millennia ago. The unwavering glow of planets. This journey of light explains one of the most useful tricks in stargazing: how to tell the difference between a star and a planet. The secret is simple. Stars twinkle, planets don't. Stars are so incredibly far away that they appear to us as infinitesimally small pinpricks of light. This makes them highly vulnerable to atmospheric distortion. Each little patch of moving air bends that tiny point of light, causing it to jump and flicker. Planets, however, are much closer to Earth. While they still look tiny to the naked eye, they appear as small disks, not single points. When the light from a planet's disk travels through the atmosphere, the distortions on one side tend to cancel out the distortions on the other. The overall effect is a steady, unwavering glow. Imagine looking at a candle flame through a piece of wavy glass. The small, sharp flame will dance and shift dramatically, but now imagine looking at a larger, glowing light bulb through that same glass. The light bulb still gets distorted, but the overall image remains much steadier. That's the difference between a star and a planet. Once you know this trick, you can put it to the test on any clear night. Find the brightest object in the sky. If it's flickering and flashing, it's likely a star. If it's shining with a calm, serene light, you've probably found a planet like Venus or Jupiter. The difference in their glow isn't just a visual oddity, it's a reminder that everything we see in the sky is shaped by what it is and how we're looking at it. The atmosphere, the distance, the angle, the type of object, all these factors come together to create the endless fascination of the night sky. Long before science could explain the physics of starlight, humans used stories to make sense of the twinkling stars. Nearly every culture on Earth has woven myths and legends around them. The ancient Greeks saw gods in the heavens, interpreting a star's flicker as a hero winking at his descendants. Aboriginal Australians saw flickering stars as the campfires of ancestors, a way for spirits to communicate with the living. In ancient Japan, twinkling stars were a sign that the lovers Orihime and Hikoboshi were happy to be reunited. These stories show how the twinkling of a star was seen as a living, magical, and often spiritual phenomenon. It was a bridge between the observable world and the imagined, a poetic way to understand the universe. Even today, knowing the science behind twinkling doesn't take away the poetry, it adds to it. It's a reminder that our ancestors weren't wrong to see a mystery in the stars. They were just looking with a different kind of eye. From ancient observers to modern science for centuries, astronomers were captivated and frustrated by the twinkling of stars. Early sky watchers in Mesopotamia and ancient Greece meticulously recorded how stars near the horizon flickered more than those overhead. They understood that starlight wasn't steady, but they didn't know why. In the 2nd century, the Greek astronomer Claudius Ptolemy noted the flickering of stars, but could not explain it. The twinkling was seen as a significant obstacle to accurate measurement. Astronomers like Tycho Brahe in the 16th century developed sophisticated instruments and even built observatories in places with thin, stable air to minimize the effect. The true breakthrough came in 1609 when Galileo Galilei used a telescope to observe the heavens. He noticed that while stars still twinkled through his telescope, planets did not. This confirmed that twinkling was not a property of the object itself, but something happening in the space between. This realization helped prove that planets are much closer and appear as tiny disks, while stars are incredibly distant and appear as points of light. Today, while the twinkling is still beautiful and poetic, it is also a nuisance for serious astronomical observation. Astronomers have developed two main solutions to this problem: mountaintop observatories. Placing telescopes at high altitudes, like in Hawaii or Chile, reduces the amount of atmosphere the starlight has to travel through, resulting in clearer, steadier images. Adaptive optics. This clever technology uses a flexible mirror and a laser to compensate for atmospheric distortion in real time, essentially de-twinkling the stars and allowing ground-based telescopes to achieve razor-sharp images. The ultimate solution, however, is to avoid the atmosphere altogether. In 1990, the launch of the Hubble Space Telescope placed an observatory above the Earth's atmosphere, providing us with stunning, crisp views of the cosmos, free from the beautiful but distracting dance of twinkling stars. In the vacuum of space, with no atmosphere distortion or twinkling, the images captured by Hubble were revolutionary, providing stunningly clear images of galaxies and nebulae. Hubble's success led to other space telescopes like the Kepler Space Telescope, which detected exoplanets by their tiny dips in starlight, a task nearly impossible from Earth. The James Webb Space Telescope, JWST, Hubble's successor, operates at a stable point in space, far from Earth's atmosphere, providing even deeper, clearer views of the universe. Terrestrial and radio astronomy modern science also uses clever techniques to overcome twinkling from the ground. Welcome to the Hypnos Helix, where curiosity finds comfort and the cosmos whispers us to sleep. I'm so glad you're here. Tonight we're taking a gentle journey to answer one of the oldest questions in stargazing. Why do stars twinkle? I hope this story helps you unwind and drift off. A fair warning though, it just might be interesting enough to keep your brain quietly buzzing. If that happens, at least you'll be learning something fascinating. Not a bad trade, right? Before we begin, a quick favor. Tapping the like button helps more people find this little corner of the internet. And if you feel like subscribing, I'd be delighted. Also, I'd love to know where you are in the world and what time it is. Are you just getting into bed, or has the night already wrapped itself around you? Let me know in the comments. Wherever you are and whatever time it is, let's get cozy and gaze up together. So why do stars twinkle? You've seen it. That gentle flicker. A star winking and shimmering like it holds a secret. It's beautiful and mysterious. But what's really happening? The first thing to know is that stars don't actually twinkle. If you were in space, floating above Earth's atmosphere, stars would appear as steady, unblinking points of light. No flickering, no shimmering, just calm, distant dots of fire. This means the twinkling must be happening between them and us, and it is. The culprit is the Earth's atmosphere, that thin, invisible blanket of gases surrounding our planet. Starlight travels billions of kilometers through the vacuum of space without a single wobble, but in the final 100 kilometers of its journey, it hits our atmosphere and things get a little chaotic. Our atmosphere isn't a stable, uniform shell. It's more like a swirling ocean of air with different temperatures, densities, and wind currents. Think of it as a giant transparent lava lamp. As the starlight passes through this ever-moving air, it gets bent or refracted. This is the same principle that makes a straw look bent in a glass of water, but on a cosmic scale. Imagine starlight passing through layer after layer of our atmosphere, each with a slightly different temperature and density. The light bends, wobbles, and jiggles. It no longer travels in a straight line, and by the time it reaches your eyes, it appears to be dancing. This effect has a beautiful name: stellar scintillation. It's a poetic phrase for a purely scientific phenomenon, the shimmering of stars caused by atmospheric turbulence. Interestingly, not all stars twinkle the same way. The ones closer to the horizon twinkle more dramatically than those overhead. Why? Because starlight from the horizon has to pass through more atmosphere. It's like looking through a thicker, more turbulent layer of air, so there's more distortion. Stars directly above. You have the most direct path to your eyes, so they twinkle much less. Even at their steadiest though, there's a gentle shimmer to them, like a distant candle flame. The steady glow of planets. Here's a fun fact, planets don't twinkle like stars. If you ever spot a bright star that seems unusually steady, chances are you're looking at a planet like Venus or Jupiter. This all comes down to their apparent size. Stars are so incredibly far away that they appear to us as infinitesimally small points of light. When the atmosphere shifts that point, you see a dramatic twinkle. Planets, however, are much closer to Earth. They still appear small, but they look like tiny disks in the sky, not single points. Even when the atmosphere distorts the light from a planet, the effect is averaged out across its wider shape. The flickering cancels itself out, resulting in a calm, steady glow. For most of human history, people saw this twinkling as something magical. Some cultures believed stars were the glinting eyes of ancestors, while others saw them as lanterns lit by gods. The word twinkle itself is so whimsical, it's no surprise it made its way into lullabies and nursery rhymes. Stars also have different colors depending on their temperature. Hotter stars are blue or white, while cooler ones are red or orange. On especially unstable nights, like a hot summer evening, you might notice a star flickering with different colors. This is the atmosphere acting like a wobbling prism, briefly separating the starlight into its individual colors before they snap back together. So the next time you look up, remember this. The twinkling isn't the star dancing. It's a message from the cosmos, a journey that's traveled millions of light years only to get its final chaotic polish from the air above your head. It's a beautiful mix of cosmic elegance and earthly chaos. Diving into the atmosphere. The atmosphere may seem invisible and still, but it's actually a busy, bustling ocean of gases, constantly swirling and stirring. To truly understand why the sky shimmers, we need to take a peaceful dive into its layers. From the ground up, we have the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. Each layer plays a part, but the one responsible for most of the twinkling is the troposphere. This is the layer closest to the Earth, stretching about 6 to 10 miles high. If you've ever been on an airplane, you've spent time in the upper part of the troposphere. The troposphere, the atmospheric layer closest to Earth, is a chaotic mixing bowl of air. It's where all our weather happens, from clouds and rain to wind and turbulence. This constant motion, caused by temperature differences, air currents, and moisture, is the main reason stars appear to twinkle.